Welcome to Moldex3D R17 Studio. In this demonstration, we're going to be going over creating a project in Studio R17. To start, we're going to open up the Moldex3D R17 Studio application. Once the application is open, you have the option to select a new project or to open an existing project. In this case, we'll open up a new project. The default name will be MDX project with the date followed. You can change this if you so desire, and then you can also change the location where you wish to save this project. Moldex3D follows a left to right approach across the top of the screen here. So first of all, we can create a new run, which the first run has been set up for us automatically. We'll select the molding type. In this case, we'll just use injection molding, but here is an example of a few other types of processes that we offer. And then we can import the geometry. Once importing the geometry, you'll automatically be kicked over to the Model menu, or the Model tab. The Model tab is where we're going to set up all of the components and attributes used in Moldex3D. So again, going from left to right, we can check our geometry to see any sort of minor errors that might be involved in our model. We can see here that we have a couple of errors. The first one is tiny edges. So tiny edges are simply small edges on our part. These small edges can cause the mesher to refine unnecessarily, and it can cause the mesh size to be different across the different regions of our part. We try to avoid this as much as possible, and we can fix a lot of these errors in CAD Doctor. The CAD Doctor integration button here will send us over into CAD Doctor, where we can select a series of different errors and also fix them. CAD Doctor is a very easy software to use. Once the model is imported, all you have to do is click Check, which will run through a 16-step checking process. The 16-step checking process will look for all different types of errors on your part. These errors will be listed under different severities. There are 3 different severities in CAD Doctor. There are critical errors. We always recommend to fix any critical errors that you find in your model. There are serious errors. Serious errors are highly recommended to be fixed if at all possible. And then there are minor errors. Typically, we don't mess with minor errors too much, as they don't cause any errors in the meshing. The whole goal of CAD Doctor is to make sure that our meshing life is as easy as possible and as fluent as possible. So if there's any errors that aren't going to cause any problems in the meshing, then there's no need to fix them in CAD Doctor. The next button that you would click is Auto Stitch. Auto Stitch is directly associated with an error called loop of free edges. Loop of free edges will happen under 2 scenarios. Either a surface is completely missing, or 2 surfaces become dissociated. The latter condition is more common and occurs because of a translational error between your CAD system and Moldex3D. It's not uncommon for this error to show up, and the Auto Stitch tool allows us to merge those surfaces back together as they initially were intended to be. So the Auto Stitch tool will use a tolerance to merge 2 edges back together, or 2 surfaces back together. The third and final button here is Auto Heal. And Auto Heal will attempt to fix any errors that don't cause any geometric modification to your part. So when you click on this Auto Heal button, you'll never have to worry about the part being modified in any way. It's just adjusting some of these surfaces to be more aligned with what Moldex3D requires. It's not going to change any surface contours, it's not going to change any features on the part. It's just going to change maybe the connection between surfaces or some of those tiny edges that we were talking about earlier. And you'll see that in this case, there are some minor errors are left over, but the serious and critical errors are removed. And you'll see that this is the case with many of the models that you run through CAD Doctor. CAD Doctor is very good at removing a lot of these major components of our major errors in our model to make our pre-processing life as easy as possible. Once we're done with the auto heal, we can simply click on export, and that'll bring us back out to Studio. Once we're back in Studio, you can see that the number of tiny edges has been reduced dramatically. Tiny edges aren't necessarily an error that will always cause a problem in the meshing, but we want to remove as many of these tiny edges as we possibly can. The free edge error that we see here is actually exactly the same thing as CAD Doctor would have picked up with a loop of free edges error. All right, so I'm going to press the green check mark, and then I'll go to the next button. Again, going left to right, we imported our part, we checked the geometry, and now I'm going to attribute the part. All right, so we got into this window called the Attribute Wizard, and all I have to do now is click on the part. Once I click on the part, you'll see this attribute dropdown. The default attribute for any object brought into Moldex3D Studio is going to be none. We need to change this attribute to align this object with what we want it to mean as far as the simulation. So if I bring in my part, I want to assign it as a part. If I bring in my runners, I want to assign them as runners. If I bring in inserts, I will want to assign them as such. So in this case, I'm just going to assign the part as a part, and I'll press the green check mark. Next, I can use the model thickness. So model thickness will allow me to see what the thickness distribution on my part looks like. And you'll actually most of the time you'll see that the part will be kind of a dark blue to a light blue color. In this case, there's like a light blue tint to a majority of the surfaces. There's like a green tint to some of the surfaces as well. The reason for this is that we haven't quite created a mesh, but the model thickness tool requires some sort of mesh to tell us what the thickness is. So it creates some sort of default mesh layout, which might not be the best of quality, which is why we get a little bit of a skewed model thickness scale. So if I take the top of this scale, I can just left click and drag this scale and bring this down. You can see the color distribution on my part is gradually going to change. And I can bring this down as far as I want. I'll bring it down to this once the thicker surface on my part actually turns red. Then I can stop and kind of visualize what's the actual thickness of this wall versus what's the major thickness of my part. So it looks like we're at about 2.7 millimeters for my part, and maybe about 3.2 or 3 millimeters for this wall. Now that we have our model in the modeling window, let's go over some mouse controls. First of all, left click on the part will select it. You can see this yellow borders or these yellow feature lines indicate that the model is selected, and then we can execute certain functions on this part. If I select the part, I can then right click on the screen, and that'll pop open a menu where I can select various operations. Right click drag will be your rotate. If you hold the shift button and right click drag, that'll be a translate. And if you hold the control button and right click drag, that'll be a zoom. Additionally, if you scroll your middle mouse button or the middle mouse scroll, that will also be a zoom option for you as well. The last one is our box select, and the box select is actually very important. So there's two different box selects in Moldex3D. You can drag from left to right on your screen, or you can drag from right to left using the left mouse button. If you drag from left to right on your screen, it'll select anything that is completely contained within the box. Note that if you don't get everything completely within the box, the object will not be selected. Going from right to left, however, if I drag my box from right to left using my left mouse button, anything that interacts with this box is going to be selected. So whether it's completely contained within the box or whether it's only partially contained within the box, it will still be selected. And both those box selects can prove quite useful under certain scenarios. Alright, using the model thickness distribution that we have on our part, let's put on our gate. To place a gate, I'm just going to simply click on the gate button. You can also click on the gate drop-down to get a list of different types of gates that we can put onto our part. I'm just going to use a simple pin gate. The pin gate function will just allow us to place a gate directly on our part, and the direction of the gate will always be normal to the surface that I click on. There's no snap required for this function, and this function will always find the closest surface to your mouse, and it'll choose that surface as your gating surface. Once you place the gate, you have the option to change the inlet and outlet diameters. In this case, you can see that the green dot corresponds to the inlet diameter, which is right here, and the red dot corresponds to the outlet diameter, which is right here. And then I can change also the gate length. You can experiment with different types of gates, such as edge gates, perimeter gates, and auto degates as well, as you can see in this list. From here, I can create a runner. You can see that, funnily enough, the runner direction is actually over in the Z direction. You can see down at the bottom right corner is our axes. However, I can change this direction using the parting direction in the runner wizard menu on the left side of the screen. In this case, I would want this sprue arrow to be pointing in the negative X direction. So I'll change this to negative X, and we'll see that it's reoriented as we would expect. You can change the dimensions of this sprue if you'd like to, so you can make it a tapered sprue by changing the dimensions as they show in this picture here, D2 being the top diameter and D1 being the diameter that connects to the gate. Next, we're going to set up a cooling system. So first of all, I'm going to create a volume through which the heat to be transferred, which will be the mold base. The mold base will just be a simple block, and we can adjust the dimensions of this block as need be. So I can adjust the length corresponding to the L parameter here, and I can adjust the width corresponding to the W parameter here. I can also correspond the height using the height dimension. This box is just a single box for heat transfer. There is no parting line, and as such, the parting direction will matter, but the actual location of the parting line will not. The next thing that we're going to set up is the cooling channels. Using the cooling channel wizard, we can set up kind of a default cooling channel system, and we can use this as the building blocks for maybe a conformal system in the future. I have 5 parameters that I can input here. I can change the channel direction. I can change the diameters of these cooling channels. I can change the number of channels on the top and bottom. I can change the pitch or the distance between the centers of these cooling channels. And I can change the height of these cooling channels from my part surface. Using some of the advanced settings, using the blue arrow at the top here, I can connect these cooling channels into one single circuit on the top and bottom. I can use external hoses or internal channels to connect these together. And I can also just specify these cooling channels on one side of my mold, and then on the opposite side of my mold I can have a different cooling channel layout if I come back into this function. Once I'm done with my cooling channel layout, I can then put inlets and outlets under the cooling channels. One inlet and one outlet per channel. And then I can check my cooling system to make sure that everything is acceptable. You can see down here at the lower left corner, this is your dialog, and the dialog here says that my cooling system is okay. Once we're done with all of our modeling, then we can go to the Mesh tab where we can generate our mesh. We have some options to adjust the way that our mesh is going to be created. However, the defaults prove to be reliable. So I'm going to click on the Generate button, and you can see all of the different meshes that are going to be created for us. I'm going to generate the surface mesh in my part, then the solid mesh in my part and runner, and then the solid mesh in my cooling system. So I'll click on Generate, and that'll allow me to generate the mesh. First, we're going to start out with the shell mesh. The shell mesh is going to set up the building blocks for our solid mesh to be generated. We use a triangular type surface mesh on the surface of our part. Using that triangular surface mesh, we can create the solid mesh, which is called BLM, or boundary layer mesh. We'll chisel open this solid mesh later to see what the structure actually looks like. Once the solid mesh is created, then the runner solid mesh can be created. Once the runner solid mesh gets created, you'll actually see that around the gate there will be a refinement. This refinement ensures that there is a connectivity between the runner and the part. That nodal connection is going to allow the flow calculation to continue flawlessly. And now we can see the cooling system being generated. So we have the cooling channels. And finally, the mold base solid mesh will be generated based on the rest of the components of our design. Once the solid mesh of the mold base is generated, then we're able to click on the final check, which will allow us to move on and start setting up the rest of the parameters for the simulation. Once the final check is completed, it'll kick us back over to the Home tab where we can continue on with our simulation setup. Now we can set up the material or the plastic to be injected. Using the Material button, we'll pop open the Material Selection window where we can use any recently used materials. We can use any material in our user bank, which is a short list of materials that you might use on a regular basis. You can also use the Material Wizard. The Material Wizard is our material database, and you can see over here on the left side there are 3 tabs. The blue project tab indicates all of the materials that are currently added to the project. The user bank shows us all of the materials that we've added to our short list. And the Moldex3D bank, the red tab, is our Moldex3D database, currently sitting at just under 8,000 materials. The material database is sorted by polymer family, then by manufacturer, and then by grade name. So you can select any material that you'd like to, and you can see the various material properties along the top side. To add a material to the project, I'm going to double click on it, and that will add it. Once the material is added to the project, you can go to the Project tab to confirm that the material has been added, and then we can close out of the Material Wizard. Now this material has been filled in to the Material Selection window. Once our material is filled in, then we can go into the process. When we first create our run, a default process is selected for us based on the material we've selected, and also based on the modeling that we've included. So a default process will be given to us. However, we do have the power to modify this process. We can modify the injection pressure, or the maximum injection pressure, which is the ceiling for pressure from the simulation. We can modify things like the filling time, the packing time, melt and mold temperature, packing pressure, cooling time, mold open time, and even our cooling channel temperatures. In the very last tab, in the Summary tab, we'll be able to see our final cycle time, which would be an addition of the cooling time, mold open time, filling time, and packing time. Once I'm done editing the process, I'll click Finish, and that will allow me to save the process conditions for the simulation. Once I save the process, then I can choose what type of analysis I want to run. Typically, for a full warpage simulation, we'll use the Transient Analysis 3 option, which will run a filling, a packing, a cooling, and a warpage, all preceded by a cooling calculation to give us an initial condition for the temperature variation through the mold. I can go in and adjust some computation parameters. You can refer to our best practices document to obtain a list of recommended computation parameters. However, the defaults should be aligned with those best practices already. When you're ready to run the simulation, you can simply just click Run, and the simulation will start on your local machine. If you want to choose another machine to run the simulation on, you can do so through the Computing Manager. Once the simulation has been run, now we can actually go in and evaluate the results. To do so, I'm going to go to the Result tab. The first result that I'll look at is the melt front time. So I'm going to expand the filling section, and the first result that shows up is the melt front time. I can evaluate the progression of my melt front using the animation toolbar. I can also zoom to a particular moment during this animation using the slider or using the percentile window in this animation toolbar. And finally, I can save this video as an MP4, GIF, or as an AVI file. Another result that's typically looked at is the temperature result. The temperature result, although it is nice to look at on the surface, is more impactful in the middle of our part. The ISO surface tool allows us to evaluate results on the interior of our part. Because Moldex3D uses solid mesh, we're able to evaluate the results through the center of our part, not only on the surface. So I can use this slider in my ISO surface window to gradually peel away some of the colder material and just leave behind the hottest material in my part to evaluate where that hot material is ending up. In this case, we can see that shear heating is a big impact because the material is hotter towards the end of fill. Another result that's typically looked at is the pressure distribution. The pressure result tells us how much pressure is required to push the material through this part. So I can take the maximum on my scale minus the minimum, and that would give me my total pressure drop. I can also look at the ISO contour tool, and that'll give me an idea of what the flow progression looks like. I can increase the number of my contours, and that'll show me if I have any sort of hesitation phenomena. Going back to the temperature result, I can also clip my part, allowing me to access the distribution of temperature through the thickness. I can also clip it in multiple directions, if I so desire. And I can click and drag these windows back and forth to get the approximate location for these planes. The slicing tool is very similar, except instead of clipping off a section of my part, now I'm going to be projecting the results onto a surface. The advantage of this is I can place multiple surfaces in a particular direction. So for example, I can put 10 in each direction and be able to evaluate my temperature distribution a little bit more clearly. Using this checkbox, I can remove these planes and see things very clearly here. I can also change my scale by left click and drag the bottom of my scale and drag it up towards the top. And we can see here how the hot material is in fact towards the end of fill region rather than at the gate where we would expect it to be. I can also use the probe tool. So using the probe tool, I can place multiple point objects. Using these probes, I can use the history tool. And the history tool will allow me to plot the temperature over time. On this part. All right. So I can take my probes, I can take my temperature, and I'll take all 5 of my probes, move them over to the right side, and this will give me a nice plot in history of what the temperatures were at those particular points throughout my cycle. Using the thickness distribution function and using the probes that I just placed, I can get an idea of what the temperature distribution is through the thickness of my part. Moving on to the warpage, we can actually see the displacement very easily. So going to total displacement, this is the amount of distance each node has moved on my part. I can use the deformation function to deform this part by times 1. I can use the scale factor to increase the scale of the warpage. That'll allow me to exaggerate the trend to make it a little bit more obvious. I can export my deformed model to compare to a real part. And I can also export my animation of my warpage as well. Also, another very powerful tool is our compare function. Compare allows us to compare either multiple runs or multiple results to one another. So what I can do is I can take my total displacement result and throw it at the top right corner. I can take my X displacement, my Y displacement, and my Z displacement and compare those to my total displacement to get an idea of what's actually causing this sort of trend. I can either sync the angle, which will allow me to keep the rotation angle the same between all my models. If I'm comparing multiple runs, I can actually sync the result between the runs to make sure that I'm comparing apples to apples. And if I'm comparing different runs, I can also sync the range. That will allow me to compare the results using the same data range, which might give me a more obvious comparison using the color distribution on my part. Finally, looking at the stresses of my part, this residual stress can then be exported to an FEA software to run a more mechanical strength test on this part. We can do that through the FEA interface. Thank you for viewing this Moldex3D R17 Studio tutorial, and we hope to hear from you soon.